So, we're still on the chapter of absolute maximum and absolute minimum. Not double integrals yet. We're gonna start it right now soon after this one problem. Partial derivatives. There is a problem I made YouTube video about. You will have it in your homework. This is from your homework. The coordinates, find the coordinate on the plane which is the closest to the origin. I made video on this and you have it in your notes now. And it's totally your homework problem. And now let's do this one. I could just make a video for this and force you to watch. But it is complicated. So I decided it's worth showing you in class to find absolute maximum and minimum with a more complicated restriction like a rectangle, circle, or any kind of different domain. It looks like so. This is a different example, but this one is a nice visualization. If you have a surface, but then you only need a domain on some kind of circle or square, then on that restriction, where is the minimum, where is the maximum? How to find local maximum or local global maximum minimum on the restricted domain? We did it in calculus 1, but in calculus 3, it's 3D, so it's complicated. And that's what I'm trying to teach you right now. In this case, it's rectangle. And this makes sense. So if you lost someone in the forest, the helicopter is flying through the mountains, only this circle that helicopter can see will be your domain. So you're looking at that person, for that person on that particular domain. That's what is happening. Let's do it. Let's sketch the graph. So there is a surface. Surface is x squared minus 2xy plus 2y. And it is need to be only checked above the rectangle R. This is a fancy way to write down a formula of rectangle. You need to learn how to read it. STEM majors, we do it quite a lot. So again, there's a surface above all of this, right? A surface, some kind of shaped. It has its own shadow, maximum and minimums, but we need to look only at the rectangle. Rectangle is x is from 0 to 3, so x is from 0 to 3. Y is from 0 to 2, so a little bit shorter. From 0 to 2, together it builds a rectangle. That's why this is a notation of rectangle. Let's call it R. How do we find maximum minimums? The step 1 is always the same. Find critical points. Step 1. Critical points. How to find critical points? You find derivatives. I will go fast here because I assume you are very good in finding derivatives now. Partial derivative with respect to x. Today we're going to be undoing partial derivatives, which means integrating with respect to x. 2x minus 2y plus 0. Partial derivative with respect to y minus 2x plus 2. Agree? So I'm going fast. Zeros and d and e's. In this case, only zeros. You solve them simultaneously, right? So I will do, usually, in my mind, I see it like so. Solving it simultaneously means, okay, let me find x from here and plug it up. X from here is 1. And I'll plug it over here. Then I will have 2 minus 2y equals to 0. That gives me y equals 1 as well. So now I have a point. X equals y, and both are 1s. So critical point is 1, 1. Lucky that we have only 1 point, which doesn't make the situation much easier. You'll see why in a second. For the absolute maximum, okay, what was the question? I forgot. But they asked to find absolute maximum and minimum. So for the absolute maximum, you don't need to do the second derivative test. That's a pro, because it's on the restricted domain. But now you have to check endpoints. Do you remember how they did it in calculus 1? We did not do second derivative test. We listed everything. We listed all, we made a list, critical points and endpoints. That's what I was teaching on Friday in my calculus 1 class. It's called global extreme values on the closed interval, if you remember. Listing critical points and then endpoints. That was in a domain. But endpoints in 3D are whatever used to be in 2D, the shapes. In this case, it's a rectangle. So we need to list critical points and boundary sides, right? Sides. In this case of R, but maybe it's a circle, so I don't like writing sides. Boundaries of R. And these consist of 4 segments. You like what? Let's see why. It's a rectangle. We just sketched the graph. We need to know all details about this rectangle. Rectangle from 0 to 3 and from 0 to 2 has 4 segments. Let's name them. For example, the order doesn't matter. L1 to the right. L2 is from 3 to 2, from height 0 to 2. L2, L3, and finally L4. Those are called segments, yeah? So, find the maximum and minimum on each line segment. For you to understand, maximum, minimum might occur here, or 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 here, and that makes it complicated. That's why this problem is more complicated. Maximum and minimum might be a pit inside of this rectangle in 3D, or it might hit the edge of the rectangle. So we have to check all of them. So that is time consuming. Let's do it. Step 3. Find maximum, minimum of the function on each segment. Why is my M so? Yes, good. Segment. Case 1. On L1, let's do L1 first. L1. And now you need to be a smart geometrist. And you're like, what? No way, we don't like geometry. No, it's fine. On L1, what can you say about X, or, and Y?
Y is always 0.
Y is 0. Amazing job. You see, L1, Y is 0. Y is 0. The height is 0. And then X is from 0 to 3. So I'll write down X is from 0 to 3. So that's what we can see. That's how I would describe it to a blind person. I would say you don't see it, but mathematically I can describe it to you. There is a segment which has height 0, and it is on the x-axis from 0 to 3. And a blind mathematician will understand it. Makes sense? Because we had actually famous blind mathematicians, specifically in Russians, and then the classmates were helping him to understand this by explaining mathematically, and then he became one of the most famous mathematicians in the world later, being blind.
What about a deaf one?
What?
There's a deaf mathematician. What about a deaf and blind mathematician?
Color blind in graph theory, that is hard. So we do, let's do the minimum. So let's find the minimum and maximum. But, that's before this. Why do we need this information? Because now we can plug. Then we can plug this information that y is 0 into f x comma y. Now we can say that, actually y is 0. Plugging 0 gives me x squared minus 0 plus 0, which is just x squared. And it should be on 0, 3. Let's not forget. So x is between 0 and 3, x squared. But y is 0, so it cancels out. Let's minimize. So basically, you need to minimize, and maximize this function x squared on 0, 3. We know how to do it from calculus 1. you find derivative critical points and then list them, blah, blah, blah. Or you can make a shortcut. You can just be smart and see what will be the smallest value of x squared from 0 to 3. 0, right? So either you actually do the whole procedure, you find derivative, which will be 2x. You set it equal to 0, gives you 0. Then you make a list, 0 and 3, and check which one gives you the maximum minimum. So this is literally global x, let's do global min max, that's shorter, min max in 2D. So check calculus 1 video. I also have videos about that. Or you can just use your imagination. It's good for easy functions, right? X squared is going up and down. It's a parabola. At 0, it is the smallest one. So x equals 0 definitely is the solution for the first one. How about the maximum?
X equals 9.
3.
X equals 3.
3. It's not always the case. Maybe 2 make it bigger, but you can check that it's not the case. It's either 0 or 3. So x equals 3 gives you the biggest maximum. And then you plug it back into the original and you get f at 3, 0. Oh, that's second one. F at 3, 0 gives you 9. That's what you meant. And then the first one, 0, 0 is 0. So let me color code it. 0 and 3. So now we even have outputs. These are our candidates. So these are local minimum, maximum, and then we're going to have to find who is the winner. Case 2, let's move on a little bit faster. Case 2. L2. Okay, now I'm going back to this picture. How would you describe L2 to the blind person?
X equals 3, y equals 0, 2.
Y is between 0 and 2. What do you think? Yes, no? So if you say to a blind mathematician, will they understand? Yeah. This is exactly how would I explain. I'm not necessarily blind. If you explain it to someone who doesn't speak English, you write it down. I will just write down x equals 3, y belongs to 0, 2. They will understand this. That means this L2. So let's write it down. X equals 3. X is fixed now, but y is keep growing up and down between 2, 0 level and level 2. Repeat the whole thing. You plug. Now you plug 3 into the original function. It gives you 3 squared minus 3 squared minus 2 times 3 times y plus 2y, which gives you, now it's a linear function, 9 minus 4y. Used to be a quadratic function, x squared. Now it's 9 minus 4y on 0, 2. So you need to figure out what is happening between 0 and 2. Same thing, you want to minimize and maximize 9 minus 4y on 0, 2. So either you find derivative and do the whole global minimum on the closed interval thing, or you just see that y is negative. So the bigger your y, the smaller the output. So what is going to be your minimum then? At where? 9 minus 4y is a line going down.
Y equals 2.
At 2, it will give you the largest input with a negative sign. That's the smallest output, right? Does that make sense?
Yeah.
So y equals 2 gives you the minimum. And then f of 3, 2 is the output for that minimum. How does maximum? This line is decreasing. So the smallest input you will plug, the highest point you are at, which is 0, right? Y at 0 gives you maximum. 3, 0 is 9. 2 more left. But I will stop for a second. What do you think?
Yeah.
Not too bad, yeah? It's kind of like very interesting. We never done anything like this before. And when I was learning this, it looked very confusing. So I like to teach it, to explain it. It's not too bad, just a little bit, many steps. How would you describe to a blind person L3? L3 is the hardest one, I would say. But maybe not. What do you think?
Y equals 2.
Y equals 2. Wow, you guys are smart. And then X? From 0 to 3. Good job. Y equals 2 and then X from 0 to 3. So height is fixed at 2, but x's keep running from 0 to 3, and that's exactly describes a segment. Repeating the whole process, f of x comma 2, I will skip the calculation, gives me x minus 2 squared. There's a full square going on 0 and 3. Now, same thing, we need to minimize and 0 and 3. Minimize and maximize that. So, minimum and maximum. Maximum makes sense because the bigger, let's see, for the maximum, actually both are pretty interesting questions. What do you think? If you plug 3 minus 2 is 1. 1 squared is 1. Is this the biggest number we can get?
No.
What is the biggest number we can get?
0.
So for you do minimum, right? For minimum.
Oh.
What number we should plug in to get the smallest output?
2.
2, right? If I plug 2 minus 2 squared, it gives me 0. So either you're guessing it, which you're not supposed to. You're actually supposed to perform the global maximum analysis, which is find a derivative that will be 2x minus 2 chain rule equals to 0. X gives you 2. This is a critical point in 2D. So we're going back to calculus 1 class here. And then you have a list of 3 points. You have a list of 3 points, and 3 points you should check. X equals 2, x equals 0, and x equals 3. You're making a list. This is how I teach it. You plug them all into your original function. 2 minus 2 squared gives you 0. 0 minus 2 squared gives you 4. 3 minus 2 squared gives you 1. There's a theorem says that there's no other points to check. Either it is in the critical point or at the end points. Those are my end points. You just choose the biggest and the smallest one. This will be my global minimum, and this will be my, and the second one will be my global maximum. The input was 2, and the output is 0 for the minimum, and then 0, 4 for the maximum. So that was calculus 1 over here going on. Calculus 1. Finally, case 4. Case 4, which is the last line, I think the easiest one. L4. Going back to the picture, how would you describe L4? How would you describe x equals 0? And then it's infinitely up and down, so you also need to add that y is restricted. X is 0, but y is keep running up and down between 0 and 3. This will be the easiest one. 3 or 2? 2. Because you plug 0, which is convenient. F0y gives you 2y, but y is restricted. That's why you call it a restricted domain from 0 and 2. This is a line that now it's increasing. So you don't have to do the first derivative test. You can just guess the minimum and the maximum. Since it's increasing, the minimum will be at the minimum input, which is 0, 0. Since it's increasing, the maximum will be the maximum input, which is 2. So 2 and 2 times 2 is 4. Make sense? Do you agree on this? These are candidates. So let's finish the step. What did I use for steps? Step 3. This is step 4 now. Step 4, the last one. So our candidates. Let's list all the candidates. You can list them in the list. We have critical point from the very beginning, which was at 1, and 1, it gives you 1. Let's build a rectangle again. Here is the rectangle. We're using, here it is, x and y. 1 and 1 is, so if this is from 0 to 3 and this is from 0 to 2, 1 and 1 is somewhere over here. 1, 1, and then 1 height goes up to the surface. You plugged into the original 3D shape. So it goes up to the third surface. Then we found also other points. which are 3, 0. So we also have 3, 0, and we need to find the output. We also have 0 and 2. Let's find them. This 3, 0, 3, 0 was found from whatever last segment 1, segment L1. 0, 2 was found over here. 0, 2 from this last line. Some of them match, as you can see. 2 and 2. Let's do last, just a second. So we need to find these. F, so these were couples. F of 2 and 2. 2 and 2. And we also have 0 and 0. And we also have 3 and 2. So 2 and 2 is actually not on the, it's not in the corner, but it's also not in between. It's still on the edge of the, this was the unique case for the parabola, if you remember. It was on the edge, but between corners, 2 and 2. 0, 0 was expected to show up. 0, 0, here it is. Let me put in blue. 0, 0. Finally, the last one was 3 and 2. That is this corner. 3 and 2. So all corners are candidates. And there are 2 points. One is in the middle, the very first point that show up. And the one is in the middle of the interval from this segment number 3. And we actually described them. We described them as local minimum and maximums. So these were candidates for maximum. Again, those are candidates. So we still don't know. We have to choose the biggest one. These 3 are candidates for minimum. And now you have to find all the outputs and choose the winner. Yes.
What about like the other maximum from like case 3? Like there's a 0, 4.
Let's see. Case 3, 0, 4. Oh, that's true. Interesting. Let me see. Where did it go? 0, 4. Did I just forget to mention? Oh, isn't it not in a domain? 0, 4.
Oh.
0, 4. No, just a second. Let me check. Yeah, good point. 0, 4 got kicked out. And that's a good point. You see, he noticed. How about this one? This one not in a domain. Why? Because X, let's see. X is from 0 to 3. Y is, oh, interesting. Yeah, it's not on the rectangle. 0 and 4 is like over here. That's why I see.
Last time we didn't do 2 and 4. So it's not.
Yeah, that was not on the domain rectangle. That's fine. Yeah, good point. So we have these, and just like in calculus 1, we're making a list, plugging all of this into the original 3D shape, 3D function, which was, I'm going back in my slides. Here it is. So making a list, and then you plug into f of x comma y, the very original one, which is x squared minus 2xy plus 2y. Plug it in, and now you do just like in calculus 1, choose the winner. So f of 1 and 1 is 1, 3 and 0, if you plug, gives me 9, 0 and 2 gives me 4, 2 and 2 gives me 0, 0, 0 gives me 0, 3 and 2 is 1. So what is the largest height on the shape, which is called x squared minus 2xy plus 2y? 9. So let me make it beautiful in the box. This is max. This is rainbow box. So we have the absolute. So these are local maximum minimums. They're candidates to be the global one. The absolute maximum is happening at 3, 0, and the height is 9. Someone asked me last class, can we do the 3 coordinates? And I said, no, I don't know why I said that. You should do that. You should do 3 coordinates, 3, 0, 9. It makes sense. Someone asked me last time, and I already blinked out like last couple seconds of the class. X, Y, Z. X, Y, and the output Z. 9. Yes, you should do that. Then, absolute minimum. Which one do you choose? 2, 2, and 0, 0, right? So let's make a smaller one and build. This gives me global minimum, and this gives me global minimum. Why not? There are several places that we can have a minimum. So we will have a point 2, 2, and the height of the minimum is 0, and then 0, 0, and the height of the minimum is 0. And that is the answer. Pretty cool?
So
Yes.
it's still called an absolute minimum if there's multiple?
Yeah, still. Because it's the biggest. The definition of the absolute one is the biggest one or the smallest one. If there are several, the biggest one, the smallest one, it's still fine. Imagine function sine or cosine, or a ribbon made from the sine and cosine. They will have infinitely many absolute maximums and absolute minimums. Yes?
For case 4 for the max, why did we put 4 for the y? Because didn't we plug in 2?
So we plug in 2. We plug in 2, and then 2 times 2, right?
Right. But wasn't 0 or x?
Let me see. 0. So you're agreeing 0 and 2, right? And then, no. So this is always about this variable y. Yeah. The x is fixed, that is x, 0. Y is not fixed, it's running from 0 to 2. The minimum will be at the smallest number because it's a line to y. At 0, x, 0, y end up to be 0 because 0 times 2. And then maximum was 2, so we plug,
It should be 0, 2, right?
we plug in, I will show you like this. F, 0 is fixed, and now we're plugging 2. That is y. 2 times 2 is 4.
Yeah, but that would be the function f02. The output would be 4, not the coordinate.
Ah, that's what you mean. I see.
0, 2.
I see. But I mean the point, though. But yeah, good point. Yeah. This is the point, and then this is the output. Yeah. I see the confusion here. The notation. So this is the problem in your homework. You'll have to do it on the rectangle, on the circles. And I just showed you one of the examples is on a circle. You see? It looks like so. Minimize this shape with this circle, x squared plus y squared equals 1, unit circle. So the shape looks like this folded piece of paper, but on top of the circle. Now you have to ignore all other shapes and see the minimum maximum on that circle. So this is the heat map or contour map. And it gives you solutions, to be honest, which is nice, you see? So if you know how to use Wolfram Alpha or Python, you can do it, but you need to learn all those steps and to know how to figure this out. Yes?
Real quick, I have a question. On case 3, our min was 2, 0, right? So if that's in the domain, why is that not like one of our options?
2, 0 is in the option here. Let's check it. Should be. Oh yeah, why it's not? 2, 0. X equals 2. Y is 0. X equals 2. Y is 0. Yeah, why it's not here? Maybe we forgot.
I think we wrote it back.
Oh, maybe. Let me see. Y. Oh. This is the one. I see. Yeah, I keep getting confused this idea. X 0. So y. X is 2. Yeah, we chose x to be 2, but y is 2. That's the point. Yeah. X is 2 and y is fixed. This is not the point we need. This is just to check.
That's the output, right?
Yeah, that's like the outputs we don't really need. We just use them to check which one gives you biggest one, which one gives you smallest one. So this is how we identify them. But this point is actually 2 and 2. Yeah, I see the confusion. This is 2 and 2 because y is fixed as 2. Yeah. That's why it's a confusing problem. I knew there will be things here. Not too bad. So don't forget you have extra credit for your homework.